Chapter 5, Loops, last video, 100% on the let's go. What are we covering here? We're going to cover break and continue, although we've already seen break. We're going to talk about some errors that can occur, some numerical errors that can occur if we're not careful on how we use our loops. And then we're just going to cover two other examples. The final one's going to be a longer one, more complicated, so I want to save about 10 to 15 minutes there. So break and continue. These are two means that we have of getting extra control within our loops. Now we've already seen break, right? We jumped ahead previously and we saw what break does is when we use it inside a loop with an if condition as part of a Boolean expression. If we see that that Boolean expression is true, for example, and then we type break, what it does is it stops that loop. It stops the loop in its tracks and we break out of the loop. So maybe the loop is running indefinitely and you want to have some condition that you're checking to determine if you should exit the loop. If that condition is true, you type break and the loop will terminate immediately in its tracks. So here's an example. It's a silly example maybe, but we're just going to loop while number starts at 0 and goes up to 20. And what's effectively happening is we're just going to sum up the numbers from 1 to 20, right? Notice that sum starts at 0, number starts at 0. While number is less than 20, we're just going to add 1 to number. So number started at 0, so now it becomes 1. We're going to add 1 to number. We're then going to take whatever's in number and add it to our sum. And we're basically going to keep doing that over and over again. Adding 1 to the number, now number becomes 2, adding that to sum. Add 1 to the number becomes 3, adding that to sum. So we're basically going to sum the numbers from 1 through 20 and add that result into the variable sum. However, because of this if statement, we have a but. We're not going to maybe make it all the way to 20 or to where number is 20 because we have a statement that says if the sum ever reaches greater or equal to 100, or better yet, once we get a value in sum that is greater or equal to 0, stop looping. There's no need to even continue. And so if you were to type this into Thonny and debug it, you would see that it would keep looping, like I mentioned. Number starts at 0, then 1, then 2. When number gets to 13, is 13 less than 20? It is. We're going to make number become 14. We add 14 to sum, but then finally at that moment, we're going to check, is sum greater or equal to 100? And because sum will be 105, we're going to break. And we're going to see that the number is 14 and the sum is 105. Maybe a silly example, and really we already know break pretty well. What we haven't seen is continue. What does continue do? Continue will terminate a given iteration. I'm pausing for emphasis. So while break will terminate the entire loop, continue will terminate a given iteration, or you can think of it as it will break or stop the given iteration, and it will then continue at the next iteration. So for clarity, continue does not terminate the loop. Continue only terminates the current iteration of the loop. So while break will break out of the entire loop, you can consider that continue that it breaks out of the current iteration. So what really happens is when you see continue, what happens is the program will then jump to the end of the loop, skipping any other lines of code. And maybe there's like 20 lines of code inside the loop. Well, imagine at line 8, we say continue. We're going to skip lines 9 through 20. We're going to go all the way to the end of the loop, and then we're going to just restart the next iteration. So here is that same example, but now we're using continue. Here we're saying sum those same numbers from 1 up to 20, apparently not counting 20. From 1 to while it's less than 20, sum up those numbers. And we don't have that statement that says, hey, if the sum is greater than 100, break. We don't have that. We're going to sum all the numbers from 1 through 20, but not counting 20, so really 1 through 19, with one condition. If number is 10 or if number is 11, we don't sum it. Notice it says continue. So think about that. We're going to add every number to sum. Add 1 to sum, add 2 to sum, add 3 to sum, 4, 5, 6, 7, 8, 9. Add those numbers to sum. But if number is 10 or number is 11, we typed continue. What does continue do? Continue will skip this final line 8 that is inside the while loop. It'll skip it and it'll restart the next iteration. So let's look at if just the number was 9. If number, well, started at 8. If number was 8, we add 1 to 8, it becomes 9. This line 6 will not be true. It's not 10 or 11 because number's 9. We now add 9 to our sum. We execute line 8, we add 9 to sum. So now we come to line 4. Is 9 less than 20? It is. Cool. Let's add 1 to 9. 9 becomes 10. If number is 10, it is. So what do? What we do is we continue, which means we skip line 8 and we come to line 4 again. Is 10 less than 20? It is. So now we add 1 to number. Number becomes 11. And line 6 is still true because number's 11. So we continue again. We skip line 8 again. We don't add 11 to our sum. We come to line 4 again. Let me put this pointer on. We come to line 4 again. Is 11 less than 20? It is. We add 1 to number. Number is 12. Line 6 will no longer be true, and we're going to add 12 to number, 13 to number, 12 to sum, 13 to sum, 14 to sum, all the way. We're going to add 18 and 19 to sum. So what does continue do? Maybe this is a silly example, but it just skips the rest of that iteration, and it continues at the next iteration. So when do we use break and continue? Short answer is you're the programmer. You use it based off of the solution or the algorithm you come up with. Certainly what we've seen is whenever you're having a lot of these programs that you have a while true loop, often we'll put the condition inside the while true loop and we'll say, inside the while true, we'll say, if such and such is the case, let's break out of the loop. That's very common. To be honest, continue is not as commonly used. It's commonly used, but there's less use cases of continue as there are for break. They're both common, but continue, when do you use it? The answer is you use it when your program or your algorithm really dictates the use of at a given iteration, hey, we need to stop this iteration in its tracks and go to the next iteration. Another answer given is you simply use it when it makes your code easier. So I'm going to show 2 quick examples, one with break, one without break, and you're going to see very clearly that the one with break makes a lot more sense. Given an integer as input, write a program that will find the smallest factor of that integer other than 1. So for clarity, if I come over here to the tablet, if I have the integer is, let's just say, what would be a good number? 15. No, let's do 15. Fine. What happened here? I've never seen that. Back. There we go. So let's say we have the number 15. And we want to find the smallest factor. Well, the smallest factor of 15 is 1, right? 1 is a factor of 15. You can divide 1 into 15. It's a factor. So it's the smallest. But we want to find the smallest factor other than 1. So then you say, okay, well, let's check 2. Does 2 divide 15? And the answer is no. Then you say, okay, well, check 3. Does 3 divide 15? And the answer is yes. 3 divides into 15 perfectly fine. And of course, as we know, that really means 15 mod 3. Does the remainder equal to 0? So we want to, given an integer, we want to find the smallest factor of that integer other than 1. So here is a solution. We ask the user for an integer, and of course we want the integer to be some value greater than 2 so the program will work. Let's say they entered 15. Well, we need to start our loop, start our checking, right, with 2, then 3, then maybe 4 and 5 if you needed to, right? Let's just say that the given integer, let's back all the way out, erase this. Let's say the given integer that the user entered was 7. Well, in fact, when you try 2, does 2 divide 7? No. 3, does 3 divide 7? No. 4, does that divide 7? No. 5, 6, 7, does that divide 7? No. We'll never, 7, of course, will divide 7. That was obvious. 7 will divide 7. So at some point, you'll get a factor, but the smallest factor might be the number itself. So we can see that we really just want to keep looping, testing all these numbers, testing starting at 2, then 3, then 4, then 5, then 6, up to possibly the number 7. And I could have done this with a for loop. Here I chose to use a while loop intentionally so we can see the usage of a while true with a break. So we have factor is 2, while true. If our number that the user entered mod our factor is 0, we found a factor, break, we're done. And then we can print out that factor. But if it's not equal to 0 when we try to divide it and we get the mod, the remainder, if that's not the case, we won't break. Instead, increase factor by 1. So now we checked factor is 3, for example. If the number mod 3 is 0, break. If it's not, let's check 4. The number mod 4 is equal to 0. Nope. And so using this example, remember, we're going to check 4, then 5, then 6, and then all the way to 7. So let's keep tracing through this. Factor now becomes 5. Is the number mod 5 equal to 0? Nope. Factor becomes 6. Is the number mod 6 equal to 0? Nope. Factor becomes 7. Whilst true, we keep entering the loop. If the number 7, mod 7 is 0, break. So we can see how this one works. It's pretty clear. The usage of a break here, instead of putting the condition in the while statement, but instead just putting while true and putting this if statement with the break, it makes sense. But what if you wanted to rewrite that same problem without a break? And instead, you want the condition to be up here of determining if you continue looping. It's a bit more convoluted. And frankly, I don't know if I even want to go through it, because when I look at this, my head hurts. Do I have a head hurt thing? Here, I'll just do this one instead, because it's just, my head hurts when I look at this. It's not something that I would choose to want to code up, because since we don't have a factor, since we don't have a break, we have to have a way of knowing should we continue. So while factor is less than or equal to n, right? So we're going to keep looping as long as factor is less than or equal to n. Well, that makes sense. So in this case, we would have kept looping while this factor 2, then 3, then 4, while it's less than or equal to 7. That makes sense. So keep looping as long as it's less than or equal to 7. But what if you find a factor? If you do find a factor, you have to have a way of exiting. Well, normally we would use break. But in this case, if we don't use break, because we're trying to avoid it to show you how it's silly to not use break, we have to have this variable found, and we set it to false. If we ever find a factor, we set found to true. So then when we loop again, while factor is less than or equal to n and not true, that would have been false and we would have exited. The takeaway, that's convoluted. Don't do it that way. Absolutely use a break and a continue. It's much easier. All right, let's jump to this program, Future Tuition. A university charges $10,000 per year for tuition. The cost of tuition increases 7% every year. Write a program to determine how many years until the tuition will increase to $20,000. So let's come over to our Thonny, make a new program. Let's call this one Future Tuition. You absolutely should be doing each one of these with me. So here, a university charges $10,000 per year. So let's start out with tuition is $10,000. Starting point of tuition is $10,000. And we know that it's going to increase 7% every year. Write a program to determine how many years it will take until the tuition gets to $20,000. So let's not start coding until we think this through at the problem solving phase. How would we solve this on paper? We know that the cost of the first year is $10,000. Well, what's going to be the cost of the next year? Let's come over here. Let's erase what we have here. So if the first year is going to be 10,000, let's just say call it year one instead of year zero. Year one is 10,000. 10,000 bucks. What about year two? If it increases by 7%, that's going to be, so if we had $100, right, 7% would be $7, and so that it would be $107 at the end of that year. Well, that would be here, 10,700. So the tuition went up 10,700 for that second year. For the third year, here's where I can't do that math anymore. What would it be for the third year? So let's come back over to here. I'm going to hit the trusty old, come on, open up. I thought I hit it. Or is it thinking? Let's see. Let me hit it again. It's probably because I have this as full screen. Nope, it didn't pop up for some reason. It's okay. I'll do it on my phone. So 10,700, what is it going to be? 10,700 times 1.07. The next year, we get 11,449. So this next year would be 11,449. Well, the program says, keep doing this. Now get the fourth year, and then get the fifth year, and keep doing each of these years until when? Until you get over $20,000, it said. So once we're at 20,000 or greater, how many years until the tuition will increase to 20,000 or more than 20,000? How many years will that take? So year zero, we said 10,000. Year one is the year zero amount times 1.07. Year two is that year one amount, which was 10,700 times 1.07, which is now 11,449, right? 11,449. Year three is that year two amount times 1.07, and we keep doing this. How many times? We don't know how many times. Which loop is perfect if you don't know how many times? The answer is a while loop. A for loop is when you know how many times. In this case, we don't know how many times. So we want to keep looping. Come back over here. Keep looping until the tuition is greater or equal to $20,000. So I'm going to do a while true. I love while true loops. Makes my life super easy. Tuition, what are we going to do? We're going to multiply it times 1.07. The math people are fine with that. Other people are like, what did you do? Well, I took the tuition, I took the current value, and I added to it tuition times 0.07, right, which is 7%. So I took the current tuition, I multiplied it times 7%, got $700 if it starts at 10,000, and then I added that 700 to the 10,000. So now I get all of this would have become 10,700, and then I save that into tuition. So this is what we had. And if you do some math here, you really realize, well, this is one full tuition. This is 0.07 times tuition. Well, that's really tuition times 1.07. That's the same thing. And of course, now if we have this, that's really the same as our augmented operator. So here we have tuition times 1.07. And after we do that, I simply need to have an if statement to check if tuition is greater or equal to 20,000, break. Now, we haven't even done the most important part of the problem though. What did the problem say to do? The problem said that it wants us to count the number of years until the tuition is greater or equal to 20,000. So you're like, oh, I got to come up here and have a starting year value. Let's say year equals, let me come back. Did they say 10,000 per year? So it's not clear here the way the problem's written. Even myself, putting myself in the mindset of a student. Is year zero 10,000 or is year one 10,000? I'm going to take a guess that it's year zero is 10,000. So now we multiply tuition times 1.07, and we increment our year. If tuition is greater than 20,000, we break. And so then finally, at the end, we need to see our output. The tuition will be doubled in 11 years. At that time, the tuition will cost this much. So here, I will make that print statement. The tuition will be doubled to 20,000 in blank years, period, dot format. This will be year. And then print at that time. The tuition cost will be this. The tuition cost will be this. And we have a period afterwards, dot format, tuition. So this is why formatted printing is so easy, because now I just come right here, and I'm going to put here colon point to F. Let's run this and see, did I guess correctly? 21048. So yeah, year 0 was 10,000, and then every year was a subsequent year. If you had said year 1 was 10,000, it'll just be off, the number of years will be off, 12 years. But that's fine. So here, at a 7% increase, tuition's going to go from $10,000 to $20,000 in 11 years. That's pretty quick, and that's expensive. All right. So this is what we came up with, and here is a solution. Is that pretty much what I did? I actually like the details on the slide. At each iteration, do 2 things. Increase tuition by 7%. What a great comment. And then increment year by 1. What great comments. Look at that. Commenting is pretty good here, but the comment was actually better here on the slide. Okay, let's see what comes next. Those numerical errors that I mentioned at the beginning of of this video. Using floating point numbers can cause numerical errors. Run this code, and it's going to blow your mind. Pause the video, type that code up, and run it. And see what you get. It's not hard to type it. Type it really quickly. See what you get, and it's going to blow your mind. Pause the video, and then come back. So when we run that, obviously, anybody can tell you, probably a second grader, when you learn decimals and digits to the right of the decimal. So here, anyone can tell you, if you take 1.0 and you subtract 0.1 5 times, anyone can tell you the answer is going to be 0.5. However, if I then come over here, x equals 1.0, and I have what? X minus equals 0.1, or just 0.1, it doesn't matter, 0.1. And I'm going to do this 5 times, 1, 2, 3, 4, 5, and then I print x. Obviously, the answer is 0.5, right? Nope. Check that out. And some of you are like, and you're like wondering, what the hell is going on? What is going on? Because that is crazy. What's happening here is limitations of the computer hardware and how 0.1 is actually stored. This is outside the scope of this course, but kind of like if we say, what is 1/3? 1/3 is what? If you divide it and you see it on a calculator, it's really 0.333333, on and on and on and on. Well, ultimately, we know that everything we type is stored in zeros and ones in binary on a computer. Well, 0.1 in binary, what does that actually equate to? What it actually equates to is this in binary, 0.00011, 0011, 0011, 0011, 0011, indefinitely. So this number, 0.1 in decimal, really equates to this in binary, which causes some issues because obviously we now have issues with what is called precision. And the fact is that we're trying to just subtract 0.1 5 times, and it can't make it happen. I'm actually curious. I haven't run this in a long time. What if I print x after each iteration? I want to see, when does it go haywire? Probably right off the bat. Let's see. No, it got 0.9, 0.8, but then right here is like, nope, it doesn't even know what to do anymore. So here, that's unique, and you'll learn more about that in a hardware course that you may take in a future semester. But the takeaway is never use floating point values as loop conditions. Consider this code. Seems pretty simple and naive. We have a sum. We start I at 0.01, and we're going to increment I by 0.01. So I becomes 0.01, 0.02, 0.03, all the way up until it is 1.0. So while I is less than or equal to 1.0, keep running this. Well, in fact, we're not going to get the desired result. It's going to be a little bit off. And the reason being is because, again, the issues with precision. So the major takeaway, you never do a loop like that, ever. Your loop should strictly be using integers. If for some reason we wanted, you wanted to add up all the numbers, 0.01, 0.02, all the way to 0.98, 0.99 to 1, you wanted to add all of that up, well, you could do so as follows, right? Starting at 0.01, we increment I by 0.01 each time, but we're not using that I value here within this while loop. Instead, with the while condition, we have a separate counter. We recognize that, hey, we're really looping 100 times, so let's just loop that 100 times with an integer counter, which I could have done here with a while loop, or here's a similar solution with a for loop. Either one of those would work. The takeaway, never, ever use floating point values as a condition, as a variable and condition within your loops. Final program. Let's go. This is a big one, but final program, and we are then done with loops. This one is using nested loops. A lot to think about here. Write a program that will find and print out the first 50 prime numbers, printing exactly 10 numbers per line. We want to come up with that output. First 50 prime numbers, 10 numbers per line, a lot to think about here. So I say break this problem into two parts. The first part is start by solving the problem of testing if a given number is prime. Now you probably have that. We've seen that multiple times already. We've seen that in the slides on a previous videos. We've maybe even solved that together, whether it be in a coding rooms or otherwise. So you probably already have that code, but we'll still talk about it. But that's not really the purpose of this problem, to identify if a given number is prime, because we've already done that. We want to use that code of how to test if a given single individual number is prime. How do we use that code to now find the first 50 prime numbers? So we want to start by solving if a given number is prime. We've done that. Once that's now done, we want to wrap that in a loop. And now we want to somehow find the first 50 prime numbers. So we need to check all of these numbers. Check 2, is it prime? Yes, it is. Check 3, is it prime? Yes, it is. Well, now we found 2. Check 4, is 4 a prime number? Nope, it's not a prime number. First of all, maybe I'm getting ahead here. What is a prime number? Coming back, hopefully we remember. What's a prime number? A prime number is a number that is only divisible by 1 and itself. Those are the prime numbers. So for example, if we look at the number 7, 7 is a prime number because what can divide evenly into 7? Only the number 1 or the number 7. I'll just edit the 1. Or the number 1 or the number 7. No other number, 2, 3, 4, 5, 6, none of those numbers divide into the number 7. If someone tells you the number, I don't know, let's pick one. How about the number 26? Someone tells you 26 is prime. You say, okay, let's test it. And you start by saying, well, we know that a prime number would be divisible by 1, and it would also be divisible by 26. But if you tell me that this number 26 is prime, it can't be divisible by any other number. So let's just start with the smallest. Start with 2. Is 26 divisible by 2? Yep, it is. Well, you're like, damn it, that's not a prime number. That didn't work. So that's how this would work. Let's check one more. How about we pick the number 9? Someone tells you the number 9 is a prime number. You're like, cool, let's check. We know if it's prime, it's only divisible by 1 and 9. So we check 2. That doesn't work. 9 is not divisible by 2. Then you check 3. And we see that 9 is divisible by 3. So this is not a prime number, right? So just a reminder of what are prime numbers and how we find them. So we need to find 50 prime numbers, the first 50. So starting at 2, 2 will be prime, 3 is prime, 4 is not, 5 is prime, 6 is not, 7 is prime, that's 4, 8's not prime, 9 is not prime, 10 is not prime, 11's prime, that's 5 numbers, 12 is not prime, 13 is a prime number. That's now, what is that, 5 numbers or 6 numbers? So we want to keep doing that. We want to keep checking all of these numbers. How many will we have to check? I don't know. That's going to be a while true loop, or at least a while loop. Keep checking over and over all these different numbers until when? Until you found 50 of them. So every time we find one, we're going to increment. Aha, I found a new prime number. This is the overall strategy and the idea of the problem. So I'm going to come back to here now. So the problem says find 50. So how many numbers will we need to test? We don't know. So that's going to be an open-ended while loop. Let's code this up. But here's the code. I'm giving you this code directly because we've seen this before. This is the code to check if a given number is prime. So let's come over here to Thonny, File New, Save First 50 Primes. And let's just type this code up. A number to check if it is prime. You know what? I'm going to pause the video. No need to even waste that time. I would encourage you to pause right here and just code up this into Thonny. So let's go check this now over in NetBeans and make sure that we understand how this is working. So here I just picked a number 23 because I know it happens to be prime. And let's look at what's going on in the for loop. And even before the for loop, I have this variable is prime that I set equal to true. Why did I do that? What I'm really doing is I'm saying to myself, whatever this number is, I'm going to assume it's prime. This number is prime as true. We assume it's prime. And then when we do the loop, if we ever come across a situation that would dictate that this number is no longer prime or could not be prime, we'll set is prime to false. So again, the number's 23. I'm saying that number's prime. Cool, let's do the for loop. So what are we going to do? We're going to loop and test all possible numbers except 1 and 23, right? Because every prime number is a number that is divisible by 1 and itself. So if I want to check if 23 is prime, I need to divide 23 by 2, by 3, by 4, by 5, by 6, by 7. You get the idea. By 8. I don't want to divide 23 by 1 because, of course, it's divisible by 1. Also divisible by 23. That's the definition of prime. So I want to try to divide 23 by 2 all the way up to 23, but not including 23. And notice as a variable name, I could have called this I, but it makes sense to give a good name. What I'm trying to find is a divisor. So I said for divisor in range 2, num, if our given number is ever divisible by the divisor, if we can ever divide this divisor into num cleanly with no remainder, it's not a prime number. So do what? Set is prime to false and break. There's no need to even continue looping as we drew out on the tablet, right? Let me erase this. If we want to know if, let's just say 8 is a prime number, well, once you divide 2 into 8 and you see that that works, there's no need to check 3 into 8, and then 4 into 8, and then 5 into 8, right? And 6 into 8, and 7 into 8. It's a waste of time. It's a complete waste of time. Once you know that 2 divides into 8, you already know that this number is absolutely not a prime number. So set is prime to false and break. Right here, break. So after we finish this loop, whether we broke out of the loop and the number is not prime and we set is prime to false, or maybe we never broke out of the loop and we finished it by going through all of the iterations and the number's still prime. Once we finish the loop, we need to test. Is prime. Is it still true? Is it still the value we started out with? If so, that's a prime number. Print it out. But if is prime is false, we can then print out that, hey, that's not a prime number. Else we can print blank is not prime. Versus up here, we could say blank is prime. So here when I run it, it's going to say 23 is prime. If I make it 24, it's not prime. 25 is not prime. 26 is not prime. 27, 28. What about 29? Here's 28. 28 is not prime. But if you test 29, 29 is a prime number, as is 31, right? 32, 33, 34, 36, 37 is your next prime number. 37 is in fact prime, but not 38. 38 is divisible by 2, right? 38 is not a prime number. So here is the code to give just for a single number to test if that number is prime. But that's not what we're actually trying to do. What are we trying to do? What we're trying to do is what? We want to wrap that code inside a while true loop, and we want to find the first 50 prime numbers. So we want to, let's think more detailed about what we want to try to do here. Let me zoom out a bit. Come on, work with me. There we go. It said wrap that code within a while true loop, make a variable called possible prime number started at 2. So let's come up here. Instead of having num equals 38, let's call it possible prime number equals 2. Variable to store the possible prime number. Because we don't know if it's prime, we need to check. So now all of this, we want to tab over, and we want to put it in a while true. And we want to keep looping until when? Until we find 50 prime numbers. Ooh, so that makes you realize we need a counter as well. So counter to store the number of prime numbers. The number of prime numbers, I could have said that better. Num primes equals 0. We're going to keep looping once num primes is less than 50. So you can put that here. You could say num primes is less than or equal to 50, right? Less than equal to 50. But I just like to make my while true loops. So I'm going to put this condition later on. So while true. All right. So what do we need to do? We need to test this possible prime number and check if it is prime. So for divisor in range 2 up to the possible prime number, well, that one's already going to be prime. We know that 2 is prime. But from 2 up to the possible prime number, remember, the possible prime number, what if it was 23? So this would go from 2 up to 23, but not including 23, right? So we're going to start with 2, though. We want to check is 2 prime. The answer is yes, it is prime. But if the number is mod the divisor is 0, we're going to set it equal to false, is prime to false, and we break. So now, if we found a prime number, what do we need to do? We need to print it, and we need to do what? We need to increment the number of primes to show that we found another prime number. And then finally, when do we exit the loop? Stop looping once num primes equals, well, num primes is 50. So if num primes is equal to 50, right? It's starting at 0. We're incrementing every time. If it's equal to 50, break out of the loop. Let's run this. Oh no, where's this at? Line 22. We're not printing num, we're printing the possible prime number. We need to increment that possible prime number too, right? This is going to find, num primes, it's a typo. This will just print out 2 over and over 50 times. Yeah, that's what I thought. Okay, so notice we started possible prime number at 2, and we found out that 2 is prime. Well, now we need to check 3 as the next possible number, then 4, then 5. So how do we do that? Here, increment or increase possible prime number by 1 to check the next number. So now let's run this, and we're going to get, oh yeah, I did it again. How did it not see that? Possible prime number mod divisor. Okay. So here, I've printed out everything, which is not the output we want. But if you, let's just go through this and come all the way down. So how many numbers did I have to loop through? I have 2 is prime, 3 is prime, 4 is not, 5 is prime, 6 is not prime, 7 is prime. So this looks like it's working correctly. 11 is not prime. 13 is prime. 17 is prime. 19 is prime. This is working. 23 is prime. We should come up to 29, 31, 37 is prime, 41, 43. Cool. It works just fine. So how many numbers did we have to actually go over? We had to go to 229 to get all of those prime numbers. Let's come all the way back and see the output. That's exactly what we want, all the way to 229. So we're basically done with the problem, but what did the problem really say? It didn't want us to print out if it's not prime, so I can get rid of this. If it was prime, it wants us to print just the number, and we can see it looks like we're printing the number right aligned with 5 spaces. So this is going to be colon, right aligned 5, and it's a decimal. It's an integer. Sorry, it's an integer. And we want to print on the exact same line. Now, everything's going to be on the same line. We're not going to have 5 lines. We're going to have everything on the same line. And it's only wrapping around because I'm telling Thonny to wrap my output. But it's getting me close to what I want. So what did the final nuance say? It said print 10 numbers per line. So here, I'm never printing a new line ever, ever, ever. Well, when should I print a new line? Every 10 numbers. So how could we do that? So after printing a number, print a new line every 10 numbers. Think of how you could do that. Well, we have a counter, this num primes. What could you do? This is a small little problem in of itself, which is why I said this one's a little bit complicated. We're at the finish line. What could you do here? Pause the video. Chew on that a bit. Think of what you could do. Ultimately, we want to have an if something, print that. What can you put right here? Think of what you could put and link it to the number of primes. So if number of primes is, you could do a long one. You could say if num primes, this is not what I would want to do, but if num primes is 10, or num primes is 20, or, right, let's just do that. If it's 10 or 20, see what happens. Well, it worked, mostly. If it was 10 or if it was 20, we printed a new line, or 30 or 40 or 50. Well, what else could you do? Once again, mod to the rescue. If num primes mod 10 equals 0, meaning every time it's divisible by 10, print a new line and check out what we get. We're not quite there. It's not quite what we want, but we're so close. And if you were to examine this code and try to figure out what's going on, well, here, remember, we've checked if it's prime. If it is prime, we've printed it. Then we incremented prime, and now we're checking num primes, but this is not inside here. Basically, the takeaway is you want to put this tabbed over. You only want to think about printing a new line if the number was prime anyway, right? Because if the number wasn't prime, why would you want to print a new line? That's what's happening, which is why we got all these extra spaces. So now when you run this code, we get exactly what we want. 50 prime numbers, 10 per line. Pretty cool. This is not a simple program. A lot going on here. So let me just summarize. We had here, this was the code to determine if a given single number was prime. What was that number? The possible prime number. You know, you could have started at 23. Here was that code to check if 23 was prime. If it was, print it. Well, now we're doing a while true loop, and we're checking all possible numbers. We're incrementing possible prime number by 1 each time to check the next number and the next number. If it's prime, great, print it, increase the number of primes found, and then if number of primes found mod 10 is 0, print a new line, and finally break once we have found 50 of them. That's a lot. Pause the video, rewind it, ask questions if need be. There's a lot on this problem. So here I'm going to show you the solution that is on the slides. It should look pretty similar to what I have here in Thonny. Let me make this a bit smaller and zoom out some. Should look pretty similar. Num primes found, possible prime number. I did not print that text. The first 50 prime numbers are. But basically this code looks identical as it should be. So as always, reach out, ask questions. We are done with looping. What comes next? Game changer, absolute game changer. And that is functions. Going to be a ton of fun. Until then, take care.